Hey there, science fans, Bill Nye here, and today we're diving into the exciting world of chemical reactions. But hold on, we're not just looking at what gets made, we're talking about how fast things happen. That's right, we're talking about rates of reaction. You might be thinking, rates of reaction sounds boring, but trust me, this stuff is far from dull. Understanding reaction rates is like having superpowers. It lets us control how fast things happen in the chemical world. Think about it. Want to make a cake rise faster? Need to slow down the rusting of your bike? It all comes down to understanding reaction rates. From baking delicious treats to developing life-saving medicines, knowing how to speed up or slow down reactions is crucial. So buckle up, science explorers. We're about to embark on a thrilling journey into the heart of chemical reactions. Get ready to discover the secrets of reaction rates and unlock a whole new level of understanding about the world around us. Okay, science sleuths, let's break down what we mean by rates of reaction. In simple terms, it's all about how quickly reactants, the starting ingredients, transform into products, the final result. Imagine you're making lemonade from a powdered mix. If you add the powder to water and stir, it dissolves and turns into lemonade. That's a chemical reaction. Now, how fast or slow that powder dissolves depends on the rate of reaction. A fast reaction means the reactants transform into products quickly, like when the lemonade powder dissolves in seconds. A slow reaction takes much longer, like the rusting of iron, which can take weeks, months, or even years. Scientists measure reaction rates by looking at how much reactant is used up or how much product is formed over a specific time. So, the next time you're baking a cake or watching fireworks, remember, you're witnessing reaction rates in action. Let's crank up the heat, science enthusiasts. Temperature plays a major role in how fast or slow reactions occur. Think about it. You wouldn't try to bake a cake in a fridge, would you? That's because heat gives those molecules the energy they need to react. When we increase the temperature, we're essentially giving those reactant molecules a boost of energy, making them move faster and collide more often. More collisions mean more chances for successful reactions, and that translates to a faster reaction rate. Imagine a room full of sleepy teenagers. Low temperature, not much interaction, right? Now crank up the music and energy, high temperature, and suddenly everyone's moving and mingling. More interactions, more fun, just like in chemical reactions. So the next time you're trying to speed up a reaction, remember, a little heat can go a long way. Section 4. Cranking up the concentration, more particles, more collisions, faster reaction. Hold on tight, science buffs, because we're about to dive into the world of concentration. In a nutshell, concentration refers to how much of a reactant is present in a given space. The more crowded the reactants, the faster the reaction. Think of it like a dance floor. If there are only a few people scattered around, they're less likely to bump into each other. But pack that dance floor with more people, and suddenly collisions are inevitable. The same principle applies to chemical reactions. A higher concentration means more reactant particles are packed into the same space. This increases the chances of those particles colliding and reacting, leading to a faster reaction rate. So if you want to speed up a reaction, try increasing the concentration of your reactants. It's like adding more dancers to the party. More collisions, more reactions, more fun. Section 5. Size matters. How particle size affects reaction rates. Get ready for a size showdown, science fans, because we're talking about how particle size affects reaction rates. You see, it's not just about how many particles are present, but also how much surface area they have available to react. Imagine trying to burn a large log versus a pile of sawdust. The sawdust will catch fire much faster, right? That's because the smaller particles have a much larger surface area exposed to the oxygen in the air, allowing for more collisions and a faster reaction. The same principle applies to chemical reactions in solution. Smaller particles, with their greater surface area, provide more opportunities for collisions and reactions to occur. It's like having a giant buffet table, large surface area versus a tiny plate, small surface area. More food exposed means more people can grab a bite. So when it comes to reaction rates, size matters. Smaller particles mean more surface area, more collisions, and a faster reaction. Section 6. Catalysts, the speed demons of chemistry. Hold on to your lab coats, science whizzes, because we're about to unleash the power of catalysts. These chemical masterminds are like the speed demons of the reaction world, able to accelerate reactions without getting used up themselves. Think of a catalyst as a matchmaker for reactants. They provide an alternative reaction pathway with a lower activation energy, making it easier for the reactants to collide and form products. It's like building a shortcut through a mountain range. Instead of having to climb over the top, you can now zip through a tunnel. Catalysts are essential in countless industrial processes, from producing fertilizers to making plastics. They help us conserve energy, reduce waste, and speed up reactions that would otherwise take forever. So, the next time you hear the word catalyst, remember, these chemical superheroes are the key to unlocking faster, more efficient reactions. Section 7, Collision Theory and Activation Energy Crash. Course into why reactions happen. Fasten your seatbelts, science adventurers, because we're about to explore the fundamental principles behind why reactions happen in the first place. Collision theory and activation energy. Collision theory states that for a reaction to occur, reactant particles must collide with sufficient energy and in the correct orientation. It's like playing billiards. If you hit the cue ball with enough force and at the right angle, you can sink that winning shot, but there's a catch. Not all collisions result in a reaction. Reactant particles need to overcome an energy barrier called the activation energy. Think of it as a hill the reactants need to climb before they can react. This is where catalysts come in handy. They lower the activation energy, making it easier for reactants to overcome that energy barrier and react. It's like replacing that steep hill with a gentle slope, much easier to climb. So there you have it, collision theory and activation energy, the dynamic duo explaining the ins and outs of chemical reactions. Remember, it's all about those collisions and having enough energy to overcome that activation barrier.